Algebra II 4.6b, Dependent Systems. If you haven't seen the previous videos for Chapter 4, you might get confused, and there's links in this video's description so you can watch them. Some systems of equations have no solution. If a system doesn't have a solution, we say it's inconsistent. If a system has at least one solution, we say it's consistent. And if a system has infinitely many solutions, we say it's dependent. And that's what we're going to talk about in this video. We can determine whether a system is inconsistent, consistent, or dependent by trying to solve the system. And for a system to have infinite solutions, its graphed lines need to lay on top of each other as the same line. So here's our first system of equations. We've got two equations, and you can just look at these and tell if we multiply the first one by 2, it's going to have the same values as the second one. When we multiply this first green equation by a 2, and remember you have to even do after the equal sign, we're going to end up with the same equation, 10x plus 4y equals 6. This same equation means it's the same line and this system is dependent. Okay? Take a look at this. Here's a system of two equations. When it's consistent, there's one solution and it meets and intersects at a point. If it's inconsistent, it's parallel and there's no intersection. When it's dependent, there's an infinite amount of solutions and the lines lay on top of each other. See that? All right, let's take a look at this next system of equations. Now we can look at this one and tell that if we double the first one, it's going to be the same as the second one also, isn't it? See? But if we multiply the first one by a -2, in this one we just multiplied it by a 2. But if we multiply this one by a -2, and remember, even after the equal sign, everything gets multiplied by 2, we distribute that in. What ends up happening is we get all additive inverses. That's a 0 pair, that's a 0 pair, and that's a 0 pair, and we end up with 0 plus 0 equals 0. Well, this is true for all x and y, so this system is dependent. And we can put this system in slope-intercept form and graph them. So if we put this first one, 2x plus 3y equals 1, into slope-intercept form, subtracting the 2x from each side, we get 3y equals -2x plus 1. We divide each one by that coefficient 3. And in slope-intercept form, we have y equals -2/3 x plus 1/3. When we do it to this one, we subtract the 4x from each side, or add a -4x, same thing. We get 6y minus 4x plus 2. And when we divide each term by that 6 coefficient by the y here, we end up with -2/3 x plus 1/3. That's the same slope-intercept. Remember, the slope is m, and the intercept b is at the end here. So they both have -2/3 x, and they both have a positive 1/3. When we go to graph these, when we graph the green one, it hits the y-intercept at a positive 1/3, and it's got a -2/3 slope. So we know if it's a negative slope, it's going to fall to the right. When it's a positive slope, it rises to the right. So these both have a -2/3 slope. So we went down 2 for our rise, it's a -2 rise, and over 3 for our run. We graphed the line, and this is what we got. When we graph the line for the other one, it's the exact same thing. They lay on top of each other. Now, every single place that these two lines touch is a solution. And because they're laying on top of each other, every single spot is a solution. So there's infinite solutions. See? All right, let's take a look at this set here. Here's our system of 3 equations, and what we can do is multiply this first green equation by a -1. We distribute it in, and we get -x minus 2y minus z equals a -1. When we slide the blue one over and add them together, we get a 0 pair here, we get a -3y, we get another 0 pair, and we get another 0 pair. So we get negative 3y equals 0. So now here's our new system of equations. This blue one became negative 3y equals 0, didn't it? See? Now what we can do is take that first equation again and multiply it by a negative 2. We distribute it into every single term, including the 1, and we get negative 2x minus 4y minus 2z equals negative 2. When we slide the red one over and add them together, we get a 0 pair here, we get a negative 3y here, we get another 0 pair, and we get another 0 pair. So we get negative 3y equals 0 again. Now because the blue and red equations are now identical, the system of 3 equations is equivalent to a system of 2 equations. So we don't have to list both of these, we can just list one of them. But that creates a problem. That means they're dependent because we have fewer equations than variables. We've got 3 variables, x, y, and z, but we've only got 2 equations. So that's dependent. We have to make sure there aren't any inconsistent equations because they can't be dependent if there's no solution. So remember, if a system of linear equations has infinite solutions, it's dependent. And if a system of linear equations has no solutions, it's inconsistent. Okay? Now, in our next video, 4.6c, we're going to talk about how algebra connects to geometry for 3 equations and 3 planes. I have some cool artwork to show you that it wasn't perfect, but I did my best. I'm going to add this video to the Algebra II playlist for your study guide, and there'll be a link to the Algebra I Chapter 8 Systems of Linear Equations playlist and the Grade 8 Math Chapter 8 playlist for Elimination and Substitution, and it's all going to be in the description of this video, so you can just click on them. All right? Okay, let's see how algebra and geometry connect to each other, and we're going to compare these dependent, independent, consistent, inconsistent planes to each other. All right? Hope I'll see you there. Bye.